Okay, so chapter 8 is about applying the physics that we've learned to different kinds of problems. So I think we did one problem. I think that was kind of about it. We did one problem that had to do with work. And now we're going to do a couple other problems that have to do with work. Some of them have to do with pressure. It's just a different way of applying the physics, and then we'll move on and we'll do some things that have to do with statistics. And we'll be good. So, what is this? This exercise 5. Which again is from the journal, but really I find that we need to go over the journal problems. That they're just kind of tough. So if somebody would read exercise 5 for us, please. Okay, so example 2 tells us that if the water is lifted at a constant rate, then the force needed to lift the water is equal to the weight of the water. Okay. And what's weight? Okay, so it's mass times the acceleration due to gravity. It's mg. But remembering, I guess the bigger thing to remember is that it is the pull of gravity. Okay, it's the pull of the earth on whatever that mass of water is going to be. But the thing is, it would be one thing if I was just hauling up that bucket. Okay, at a constant rate. It wasn't accelerating, which is the key there. Okay, so for those of you playing AP Physics, the work would, I frequently say that if you're staying to play AP Physics. Yeah, dude, playing it all year. Okay, remember that work is equal to the change in potential energy plus the change in kinetic energy. If it's moving at a constant rate, what's the change in kinetic energy? 0. Okay, so the work would be equal to the change in kinetic energy. However, and that's still true. But we usually think about it in physics that I'm just lifting up the bucket. But what's different about the bucket here? It's losing mass, so it's losing weight. So as the bucket rises, it's getting lighter and lighter. It has less and less weight. So the amount of work that I'm doing as the bucket rises is getting smaller and smaller. Okay, so again, if my bucket was full the whole time and there was no leak, how would I find that work? And mgh, which would effectively be F dot D, right? Okay, but I can only use F dot D when what happens? When the force is a constant. Okay, so I can't use that here because my force is changing because the mass in my bucket is changing. So what's the other expression that we have for work? It is the integral. Okay, so it's going to be the integral of f of x dx from some a to b. Which brings us back to the calculus part in example 2 and what they told us to do in example 2. So note that this is an integral over what? What am I integrating over? X, which in the real world means what? Position or distance. Okay? So I need to find an expression for the weight of the water that's a function of the distance that the bucket has risen. Okay, so that then I can integrate it and figure out what that work is going to be. Okay. AP Calc students, you understand this is the formula we're going to use, right? Okay, AP Physics, you understand why we have to use that formula and how it connects to what we did in chapter 7 and 8? Yes? Gianni? Maybe? Not quite sure you're there. That's okay. All right. So, because the water is flowing out of the bucket at a constant rate, then I can say that time, which is kind of how you'd think about it, right, is proportional to height. So that even though I might want to think about the weight of the water changing as a function of time because so much water leaks out every second, I can in fact rewrite it as a function of height because it's at a constant rate, because I'm lifting the bucket at a constant rate and the water is leaking out at a constant rate, that every second I'm moving so much height and I'm also losing that same amount of water. Okay? You with me? You got it? All right. So thank goodness for example number 2, which tells us that that lifting force, F of x, is equal to the initial weight times 20 minus x over 20. So this is my lifting force, which is proportional to the weight. And this is the proportion of the height above the ground. Okay. So I didn't pull that out of the air, I pulled it out of example 2. What's that? Okay. I love it when people answer their own questions. Okay. We good? We got it? Okay. So what's the initial height in example, I'm sorry, what's the initial weight in example 5? Yeah, 490 newtons. And then it's 20 minus x over 20. The 20 comes from the fact that we are lifting the whole thing up 20 meters. Okay. So the work done, like we said, is going to be the integral of f of x dx from some a to b. So I've got my integral from 0 to 20 of 490 times 20 minus x over 20 dx. You can, I think I actually distributed it. So I made mine look like this. So it was 490 because what I did was I made this 20 over 20 minus x over 20 minus 24.5x dx. You can do it however you like. And then we use all of our powers of integration. And what's the first thing we ask ourselves? Can we solve it by inspection? And can we? Okay, so what's the antiderivative of 490 dx? Good. And what's the antiderivative of 24.5x? And I don't really have plus a constant because it's a definite integral, so I'm going to evaluate it between 0 and 20. And when you plug those in, what do you get? What other people got? Yes, Maddie got, Gianni got. Okay. All right, we got it. Okay. So number 17, which is the next one we're going to do, is again a physics-related problem, but it has to do with pumping. And when we're pumping, the applied force is again going to be related to the weight of the material that we're pumping out. So let's do number 17. If somebody would read it for us, please. Okay, so let's just start with that. So I've got this tank. Okay. And it is 10 feet by 12 feet by 20 feet. And remember that this up here at the top is ground level. And that means that the whole tank is underground. So this top part here is even with the ground. And then the tank goes down 20 feet. So I need to pump it up to ground level. Okay. So we're going to do what we always do. We're going to take a slab of water here that has some thickness delta y, and is located at some position y, and we'll let y be equal to 0 up here at the top because that's where I want the water to go, and we'll let y be equal to 20 down here at the bottom. And then what I'm going to do is figure out the force required to move this slab up to here. And then I'll integrate over all the slabs. Or slices, however you want to put it. Okay. So, like we said a minute ago, the applied force is again going to be equal to the weight of the water. Or whatever material it is that we're pumping out. But I need to figure out what that amount of water is. Okay. Can't we just what? Yep. But the water that's down here, I have to move through a bigger distance than the water that's up here. So remember, what's work equal to? It's going to be force times distance. So I'm not taking the whole volume of water and lifting it 20 feet. I'm lifting the stuff at the bottom 20 feet, but I'm lifting the stuff in the middle only 10 feet, and the stuff that's right up at the top I may only be moving 1/10 of a foot. Yeah. I'm going to be moving this slab, which has a volume of 10 times 12 times delta y, a distance of y feet. But the thing is I want to know the weight of that water, not the volume of that water. So how do I figure out what the weight of that water is? Well, I'm going to have to use density, okay, because I need to somehow relate the volume to a weight. Okay, so they gave you this number, which was 62.4 pounds per foot cubed, which we can call density, but it's not really density. Because what is density, my AP Chem friends? Or anybody else? What is density? What is it? It's mass per volume. Is this mass per volume? AP Physics people? Weight per volume might make a little more sense. Yes, Priya. We could, but it's already in the stupid unit of feet and pounds, so we're just going to have to run with it. Nobody does. It's stupid, but it's stupid. Okay, so this is kind of like a volume. I'm sorry, this is kind of like a density, but it's not really a density because it's not mass per volume. It's actually weight per volume, which makes our problem a little simpler because remember, what's weight again? Well, yeah, but we need to make the connection for the people that don't remember what mg is. It's the force of gravity. And as Maddie said, it is also going to be equal to F applied. Okay? But we got to get it to the right place. So if what I want is the weight. How do I get the weight if I have density? Yeah, so I'm going to call it delta V because I only want the volume of my slab that I'm going to move y feet. Okay, and that's going to be times rho. So let's take a little side trip over here. And what's delta V going to be? What's volume? Okay, so volume is going to be length times width times height. So that's going to give me 10 feet times 12 feet, and my height is delta Y. And I'm going to ignore my units. So my delta V is going to be 120 times delta Y. So my weight, which I'm going to call F of Y because it's going to be my applied force, is going to be this 120 delta Y times 62 times 62.4. Which is going to give me what? Okay, good. Good. Okay. So this is the applied force that I'm going to have to use. And then for my particular slab, which is random, I'm going to need to move it y feet, excuse me, to get it to the top. So my work, which is again my integral from a to b of f of y. Do we really want to write it that way? I'm not going to write it that way. Okay, so the work done in lifting that slab, that particular slab, is going to be the force times the distance that I have to move it. Or 7,488 y delta y. No. Y is the distance from wherever my slab is to the top. So it could have a lot of different values, and it will have a lot of different values. Okay. But if I make my slab infinitesimally thin, then all my deltas become differentials. Which means I can integrate them. And I'm going to integrate from 0 to 20. And my work, I'm going to integrate from 0 to the total amount of work. So I have come to an integral. What's the first thing I ask myself? Can I solve it by inspection? Can I? Yeah. So what's it going to be? It will, and I'm going to evaluate it from 0 to 20. And so what do I get? Same thing. And what are the stupid units that it has? Well, what would you want it to be if it were SI units? And what's a joule really? Think about a joule in terms of it's the unit of work, and what's the basic formula for work when the force is constant? Nope. I want work equals bump, bump, bump. What? No, I'm giving you a hint here. The force is a constant. Force times distance, force dot distance, right? What are the units of force? What are the units of distance? So if I'm using this stupid unit system, what's the unit of force? In this problem, what were the units of force? Pounds. And what were the units of distance? Feet, except we don't say pound feet. For whatever reason, we say foot pounds. And everybody knows that LB is the abbreviation for pound. It's stupid, but it is. I have no idea where that comes from. Okay. All right, so that's part A. What does part B ask us? Okay, so they give us something in there in parentheses, right, that we need? Which is work per time, which is what? My AP Physics people. Power. Okay, power is the energy or work done or expended over an amount of time. So it's the rate at which the energy is delivered. So I know that I need 1.5 times 10 to the 6 foot-pounds of energy. I know that my motor gives this much energy every second. So how do I determine the amount of time it's going to take to have this whole amount of energy delivered? How do I figure it out? Maddie. Yeah. So it's the total work done over the power. It's the total amount of energy that I need delivered divided by the rate at which that energy is delivered. So it's going to be 1.5 times 10 to the 6 foot-pounds divided by 250 foot-pounds per second, which is going to give me what? Well, this is an intermediate answer because what is my answer supposed to be in? To the nearest minute. So yeah, so you could actually so we could actually go with 1 minute. No, wrong way. 1 minute is 60 seconds. And if you convert that, what do you get? What do you get? 100 minutes. Okay. So what's going to happen is this is going to cancel with this. The denominator of a denominator is a numerator. I heard somebody say it. So this whole thing here, is going to have units of seconds when all is said and done. Okay. All right, so there's part C. What does part C say? Okay. So 10 feet is halfway. So what do you think we should do? We're gonna draw a picture. It's always a good option, but it's not really going to be helpful. Maddie, what do you think? Okay. So I know that power is equal to work over time. So how's that going to help me? It's an excellent first step. Okay, so that means, very importantly, that I can figure out how much work or how much energy is delivered during that period of time. And then I can go to the next step. So the power is 250 foot-pounds per second, but my time is in minutes, so what do I need to do? Convert it, and I know that there's 60 seconds in 1 minute. So how much work do I have? How much energy am I going to get out of this whole thing? And it's going to be foot-pounds, because my minutes will cancel there and my seconds will cancel there. But now what I'm going to do is I'm going to back up. And at one point, back here, I had this formula, right? Okay. Except that I don't want that to be a 20 anymore. I want it to be a D. And I'm going to solve for that D. And if I'm lucky and I did it right, what should D be? 10 feet. Yeah, because it's stupid units. Okay, so this is going to be that 7488 divided by 2 times y squared, and I'm going to evaluate it from 0 to d. So 7488 over 2, d squared minus 0, but that's going to be equal to that 375,000 foot-pounds. So what's D going to be equal to? It's Priya, right? They want it to be equal to 10, right? That was the whole thing. Show that it's halfway. So that's good enough for me. Okay. Now there is a part D, but I think it's just plugging and chugging and repeating something that we've already repeated, and being that the bell is going to ring, bless you, we are not going to do that. Okay, so we will work on the rest of our examples, yeah, on Wednesday, because we've got Math Week tomorrow, and then I would suggest to the rest of you that you have the homework done by Friday, but those of you who are going to be traveling, I'm certainly not going to expect that you're going to have the homework due by Friday. Okay, but make sure you bring your white slips so I can sign them and I know when everybody's going, okay? Oh, but wait, because since you're all here, I don't know where Priya went, the break work is already in your notebook. No, just Calc. So I don't know if I've distributed it yet, but if you go up to Content Library under Review Materials, it says Spring Break Homework. Okay, And it's all in there. It's a regular kind of review sheet, and then it's this goofy thing that I found called the Great Calculus Caper. So don't Google that for the answer, but what it has you do is solve 9 calculus problems, and for the answer allows you to eliminate one of the suspects. So it just seemed vaguely interesting. So that's what we're doing. Okay? Yeah, cute's a good word for it. Okay? But that homework is there. Thank you.